Welcome to this explainer. Every time we stream a video or ask an AI a complex question, we're actually generating intense heat in a data center somewhere. Today, we're diving into the hidden engineering marvel that literally prevents the internet from melting down, the dual-loop water system. It's this brilliant, beautifully orchestrated dance between two totally different systems: chilled water, which collects heat indoors, and condenser water, also widely known as cooling water, which throws that heat outside. Here's a quick look at our agenda for today. First, we'll look at the ultimate heat challenge. Second, chilled water, our collector. Third, condenser water, the rejector. Fourth, the exchange point. And finally, we'll put the key differences side by side.
So this brings us to a really fascinating question right out of the gate. How exactly do engineers move extreme heat from inside a building to the outside world efficiently? Think about it. AI servers run 24 hours a day, 365 days a year. Without instant heat removal, they'd face catastrophic thermal shutdown in a matter of minutes. You can't exactly just open a window in a massive data center, right? And you definitely can't just dump perfectly good refrigerated water outside the moment it gets warm. The solution requires a highly orchestrated thermodynamic relay race.
All right, Section 1, the ultimate heat challenge, moving heat from the inside out.
Moving right into Section 2, chilled water, the collector, our closed-loop hero. Let's meet our first protagonist. Chilled water is our indoor cooling agent. To really understand it, we need to define its home base, which is a component inside the central cooling machine called the evaporator. This is where the chilled water starts its journey at a very brisk 7 degrees Celsius. It gets pumped directly out into the server rooms, absorbs the intense heat radiating off all that IT equipment, and cools the surrounding air right down. Now, the absolutely crucial point about chilled water is its environment. It operates in a completely sealed, closed loop. It is safely hidden away, never once exposed to the outside air. Because it's so incredibly cold, way colder than the ambient temperature in the building, the pipes carrying it have to be wrapped in really thick insulation. If they weren't, they'd literally sweat and drip condensation all over the facility, which is a massive no-go around servers. After it absorbs the heat, this water warms up to about 12 to 15 degrees Celsius and travels right back to the evaporator to be cooled down again. It just goes round and round, doing its job in its own pristine, closed-off track.
Okay, Section 3, condenser water, the rejector, throwing the heat away.
So while chilled water is busy collecting heat indoors, we have our second protagonist, condenser water, which you'll often hear referred to as cooling water. Its sole purpose in life is rejecting heat outdoors. It never goes anywhere near the actual servers. Its home base is another section of the cooling machine called the condenser. And here, the water is surprisingly warm. It usually starts its journey at roughly 32 degrees Celsius. Its specific job is to absorb all the heat that the chilled water originally collected, plus any extra heat generated by the massive cooling machinery itself, before it heads straight up to the roof.
This brilliantly illustrates the main contrast. Condenser water operates in an open loop. When it reaches the roof, it enters a cooling tower where it's literally sprayed and exposed directly to the outside atmosphere. Massive fans blow outdoor air across it, which causes a portion of the water to evaporate. And it's exactly this evaporation process that actually releases the heat into the sky. It cools the remaining water back down from about 37 degrees to 32 degrees Celsius, sending it back down to the condenser. But because it's open to the air, things like dirt, microbes, and dust are constantly getting in. That means this specific cooling water requires intense chemical dosing. And since it's constantly evaporating away, it needs a continuous, non-stop supply of fresh makeup water.
Which brings us to Section 4, the chiller exchange point, the absolute never mixing rule. You might be wondering, how do these two totally distinct loops interact without ever actually touching? We have pristine, cold water indoors and dirty, warm, cooling water outdoors. Well, this quote from our source material is the perfect analogy for remembering their respective roles. Think of the chilled water as the collection vehicle, driving carefully through the indoor server aisles, picking up the heat. But a local collection vehicle doesn't drive all the way out to the landfill. It goes to a transfer station and dumps its load into a massive condenser water dump truck. That heavy-duty dump truck is what actually hauls the heat away to the atmospheric landfill up in the sky.
I really want to heavily emphasize this point. These two waters literally never mix. They are separated by solid metal walls inside the main cooling machine, known as the chiller. They merely pass the heat through the chiller's chemical refrigerant. It acts exactly like runners passing a baton in a relay race. The refrigerant is the ultimate middleman that bridges the gap between the evaporator and the condenser, without cross-contaminating the water.
Let's break this down step by step and see how this heat baton pass chronologically flows from the servers up to the sky. Step 1. The chilled water arrives at the evaporator, carrying the indoor heat. Step 2. The chemical refrigerant absorbs that heat, gets incredibly hot and pressurized by a compressor, and rushes over to the condenser. Step 3. The condenser water flows over the pipes containing that hot refrigerant, absorbs the heat, and takes it up to the cooling tower on the roof to be evaporated. It's just an elegant, continuous thermodynamic relay.
Finally, Section 5. Key differences at a glance. Let's bring it all together.
Here is the fundamental contrast we've been talking about. On the left side, we have our chilled water, a closed loop, sealed tight, doing the delicate work of absorbing indoor heat. On the right, we have the condenser water, our cooling water, an open loop, fully exposed to the elements, acting as the heavy-duty dump truck rejecting that heat to the outdoors.
And looking at the exact engineering specs, this table really cements the completely different environments of the two loops. Look at those supply temperatures. 7 degrees Celsius for chilled water versus 32 degrees Celsius for condenser water. One is frigid, the other is warm. One is a closed loop, the other is open. One lives in the evaporator, the other lives in the condenser. They are truly the yin and yang of data center thermal management.
I'll leave you with this final thought. As our computing power grows, the sheer volume of heat we generate is rising exponentially. This means our condenser water dump trucks have to evaporate millions of liters of water to keep the internet running, creating a massive strain on local water supplies. So how will we engineer the future of these cooling loops to protect our most precious resource while still feeding our endless demand for AI? It's a massive challenge, and one the engineering world is racing to solve right now. Thank you so much for joining me on this explainer, and keep asking the big questions.